This conference will now be recorded.
Yeah, dear students, so in the last session, we have discussed about characteristic functions, moment generating function, which can generate the moment. And also, we have started with transformation on random variables, right? So in the transformation of random variables, so first we started with monotonic transformation of a continuous random variable. So in the monotonic transformation of a continuous random variable, we have also discussed about the monotonically increasing transformation. So if the relation between the random variable x and the new random variable y, if the relation between x and y is monotonically increasing relation, then how to derive the distribution function and density function of the new random variable, that is y, is discussed in the last session. So now we are moving into the other one, that is monotonically decreasing transformation. So that is monotonically decreasing transformation of continuous random variable. So how do you write this one? When you can say the transformation as monotonically decreasing transformation, a transformation T of a continuous random variable x is said to be monotonically decreasing if it satisfies the condition T of x1 greater than T of x2 for any x1 less than x2, which are the elements of the random variable x. So in the previous case, for the monotonically increasing, if at all if x1 is less than x2, and if the transformation of x1 is less than transformation of x2, that is monotonically increasing. In this case, for x1 less than x2, if T of x1 greater than T of x2, then it is monotonically decreasing transformation, right? So that is, if y is having an element y0, which is corresponding to a particular element x0 in the existing random variable x, only one element is considered, then you can write the relation between the new random variable element and existing random variable element like this: y0 equal to T of x0 or x0 equal to T inverse of y0. That relation is similar to the previous one only, but where do you get the change? So that is, this transformation is monotonically decreasing transformation. Monotonically decreasing transformation can also be represented like this. Anyway, why not? The element of the new random variable in correspondence with the element of the existing random variable, but here the transformation is decreasing transformation. Now here, how can you write? Earlier, the probability of x less than or equal to x0 is corresponding to, that is, probability of y less than or equal to y0. So in the sense, that is, to find out probability of y less than or equal to y0, we need to take probability of x less than or equal to x0 in the previous relation, that is monotonically increasing transformation. But in this case, to find the probability of y less than or equal to y0, we are supposed to take this one, that is probability of x greater than or equal to x0, greater than or equal to x0. So that is p of y. Now the probability of the event y less than or equal to y0 must equal the probability of the event x greater than or equal to x0, because of one-to-one correspondence. Not only this, if I take any element as x1, that is p of y less than or equal to y1 is equal to p of x not less than or equal to, here in this case, greater than or equal to x1. In other words, you can also write it as 1 minus p of x less than or equal to x1 for representing new element y1. For y0, 1 minus p of x less than or equal to x0. Just observe the change between increasing monotonically increasing transformation, monotonically decreasing transformation, right? So here also you can derive the distribution and density functions from the distribution and density functions of existing or original random variable x, right? So that is, how do you derive? That is, from the definition of the probability distribution function, we can write it as Fi of y naught equal to 1 minus fx of x naught, or 1 minus fx of t inverse of y naught. From the properties, I can write this Fi of y naught as what? Same as previous discussion. Integral minus infinity to y naught Fi of y dy, or 1 minus, what is this? Integral minus infinity to x naught fx of x. Or we can also write 1 minus integral minus infinity to t inverse of y naught fx of x dx. Right? So by differentiating here, I can write it as from the Leibniz rule, same as the previous one. Fi of y naught into y naught equal dy naught equal to, anyway, one differentiation is 0, minus fx of x naught into dx naught, and dy naught is, now I'm taking the dy naught into the right hand side, therefore it becomes minus fx of x naught into dx naught by dy naught. In other words, I can also write minus fx of t inverse of y naught into dt inverse of y naught by dy naught, right? So therefore, it is only for element y naught, and it is also applicable for any element, maybe y1, y2, y3, and so on. So generalized statement can be taken like this: Fy of y equal to minus fx of t inverse of y into dt inverse of y by dy, or simply you can write fx of Fy of y equal to minus fx of x into dx by dy. Same as the previous one. The only difference is this, in this relation we are getting negative sign. In the previous monotonical increasing transformation, we got positive sign. In the monotonically decreasing transformation, we got negative sign. That is only the difference between the two transformations. And you can generalize here. Why? Because the two transformations are monotonic transformations only. One is increasing, other one is decreasing, and you can standardize the relation like this. Therefore, for the monotonical increasing transformation, you can write generally here Fi of y equal to fx of x into mod dx by dy. Why? Because for increasing transformation, fx of x into dx by dy. For decreasing transformation, minus fx of x into dx by dy. Therefore, the generalized expression can be taken like this: Fi of y equal to fx of x into mod dx by dy. Based on the type of the transformation, the modulus value will be represented. Right? So this is about monotonic transformation of continuous random variable. Let us take non-monotonic transformation. What do you mean by non-monotonic? Monotonic in the sense maybe increasing or decreasing. Non-monotonic means non-monotonic transformation, there is a many to one correspondence. Earlier we have only one to one correspondence, that is a new random variable element y naught is in correspondence with only one element in x, that is x naught. Whereas in this case, the new element may be in correspondence with more number of elements in the existing random variable x. How? That is, there is many to one correspondence between x and y. That is, several values of x can be transformed into one random variable y naught, that is in the y. That is, y may have several roots. How? Let y naught in the random variable y has three values, x1, x2, x3 in the random variable x. Then the PDF of y is given by, so that is, it is the correspondence actually here. Y naught is the new element of the random variable of new random variable y, and these are all elements of the existing random variable x, right? x1, x2, x3. So that is, how do you write? Therefore, the probability of this event is given by, how do you write? P of y less than or equal to y naught equal to P of x less than or equal to x1, and in between x2 and x3, x2 less than or equal to x less than or equal to x3. Why? Because if you see the previous figure, so that is less than or equal to x1, and also in between x2 and x3. In between x2 and x3. Here, if you observe, in between x0 and x1, it is increasing, whereas in between x2 and x3, decreasing and increasing. Just see the change here. That is, y less than or equal to y naught in the sense all the values of x yielding y less than or equal to y naught. In this example, only 3 elements are taken. Maybe more number of elements may also be involved in some scenarios, right? So now, therefore, I can also say like this: P of y less than or equal to y naught equal to P of x when y is less than or equal to y naught. That is, I am transforming more number of elements in the random variable x onto the new element in the new random variable y, right? So that is, using these definitions, we can write the distribution and density functions of new random variable also. But how? Fy of y naught is equal to integral. So it is not related to only one element. Therefore, I can say it as integral x given y less than or equal to y naught fx of x dx. It may be addition of more integrations, right? So that is, how do I write? And to find the density function, if I know the distribution function, I know how to find the density function. Simply I can say dy naught of the whole distribution function fy of y naught or integral x given y less than or equal to y naught fx of x dx. Simply, or if I take the same example, that is y naught is depending on the 3 elements x1, x2, x3, or in other words, 3 elements in the x1, x2, x3 are transformed to new element in the random variable y, that is y naught. So here, how do you take the set of values of x corresponding to p of y less than t of x less than or equal to y plus dy consists of following 3 intervals. That is, one particular interval in the random variable y is relating with 3 intervals in the random variable x. What are the intervals? One is in between x1 to x1 plus dx. Other one is in between x2 and x2 plus dx. Third one is x3 to x3 plus dx. 3 intervals, right? One interval in the new random variable is in correspondence with 3 intervals in the existing random variable. In such a scenario, how to find the density function or distribution function of the new random variable? So in the previous slide, generalized statement is given. So let us go to the clear picture. That is, p of y less than t of x less than or equal to y plus dy is equal to p of x1 less than x less than or equal to x1 plus dx plus p of x2 less than x less than or equal to x2 plus dx plus p of, in the sense, probability of x3 less than x less than or equal to x3 plus dx. That is, p probabilities are summing together to derive the probability in the new random variable case, right? So therefore, generally, how can I write from the relation with density function or from the property of density function? What is this actually here? In between, the probability in between y and y plus dy, it is nothing but fy of y into dy. Nothing but fy of y into dy. Why? Because the probability equal to what? Integral y to y plus dy fy of y dy. So in other words, I can say like this: fy of y into dy. Why? Because it is a differential term. Similarly here, for the differential term dx1 here, fx of x1 into dx1. Why? Because differential term here. Fx of x2 into dx2 here, this one. And here, but here, what is this? One is monotonically increasing, second one is monotonically decreasing. Why? Because the relation is given like this. The first one is that x1 monotonically increasing, second one monotonically decreasing. See the figure here. Just see the figure. For the x1 monotonically increasing, x2 is taken where the relation is monotonically decreasing, x3 is taken again for monotonically increasing. Therefore here, what is going to get here? Minus dx2 plus fx of x3 into dx3. Or I can say like this: fy of y equal to fx of x1. I'm just taking dy from the LHS to RHS. So fx of x1 into dx1 by dy, fx of x2 into dx2 by dy, fx of x3 into dx3 by dy. But here why I am taking the mod here? So in the previous session I have discussed for monotonically decreasing and increasing, I am getting the only change is the sign change. That is for increasing transformation plus dx by dy. For decreasing transformation, I got minus dx by dy. And for representing the complete monotonic transformation, irrespective of increasing or decreasing, I can use the mod here. So similarly, I am taking the mod here, fx of x1 into mod dx1 by dy plus fx of x2 into mod dx2 by dy plus fx of x3 into mod dx3 by dy, right? So therefore here the density function, how do you write? The density function is nothing but the summation of three functions here, that is fx of x1 into dx1 by dy, fx of x2 into dx2 by dy, fx of x3 into dx3 by dy. Even if I have the fourth term, fx of x4 into dx4 by dy, and generally I can write summation n depends upon the number of elements on which the new element is having the correspondence, right? Summation fx of xn mod dxn by dy, or you can also write like this, fy of y equal to summation fx of xn by dt of x by dx, where x equal to xn. Generalized statement. Am I clear? This is the way to derive the density function in the case of non-monotonic transformation, or if I have the new element of the new random variable is having the correspondence on more elements on the existing random variable, or if more elements in the existing random variable are transforming to single random variable, the new density function can be derived using these relations. Am I clear? Right? Fine. Next one is transformation of a discrete random variable. So far we have discussed the transformation may be monotonic transformation or non-monotonic transformation of continuous random variable. Now let us move on to transformation of discrete random variable. Let x be a discrete random variable, and ultimately y equal to t of x is a continuous transformation. Continuous transformation. For the discrete random variable x, we have the density and distribution functions like this. We all know that. We already discussed about this. Fx of x equal to summation p of xn into del of x minus xn. That is series of impulses. Density function is series of impulses. Whereas the distribution function is a staircase function. In the functional way, it is fx of x equal to summation p of xn u of x minus xn. Right? So now let us move on to the new density function and distribution function. And here, if the transformation is monotonic, that is monotonic transformation of discrete random variable, there is a one-to-one correspondence between x and y, so that yn equal to t of xn. Generally, yn equal to t of xn, or xn equal to t inverse of yn. Therefore, the density and distribution functions of new random variable y are given by, how do you write? The new density function fy of y equal to p of yn into del of y minus yn, and distribution function is p of yn into summation p of yn into u of y minus yn. But how do you get these values? Again, from the existing random variable, that is where yn equal to p of xn and p of yn equal to p of xn. Am I clear? Right? So this is the way to apply the transformation on discrete random variable. If it is non-monotonic transformation, there also the same thing. In the previous case we have discussed, in the continuous random variable case, in the non-monotonic transformation, we have taken the individual relations, well, that is maybe monotonically increasing ones and monotonically decreasing ones, and all the relations are taken and summed together to derive the new density function. Same method we use here. That is, if the t is non-monotonic, the above procedure remain valid, except that there now exists the possibility that more than one value xn corresponds to a value yn. In the sense what? If more number of values are corresponding in xn, so ultimately P of yn will be equal to the sum of the probabilities of various xn for which yn equal to t of xn. Same method. So equally, individually you need to find and you need to sum together to derive the new probability value, whereas that is from that you can derive the new density function, right? Right. Let us take a simple problem based on the transformation. There you can understand better. Let the random variable x has the probability density function fx of x equal to e power minus x when x is greater than 0. Find the cumulative distribution function of y equal to g of x equal to x square. What is the relation given between new random variable and existing random variable? Y equal to x square. In the previous session, we have taken one scenario. What is that scenario? That is the relation between velocity and kinetic energy. You know the relation between velocity and kinetic energy. The kinetic energy E is the new random variable. Velocity V is the existing random variable. What is the relation between kinetic energy and velocity V? E equal to half mv square, right? That is the relation we have. Similarly here, if I have the relation y equal to x square, I would like to transform x to y. If they have the relation like y equal to x square, right? But the density function of existing random variable or original random variable is given as exponential term. What are you supposed to find here? The distribution function of new random variable, not density function. Only distribution function is given. So can you try it? How do you find from the discussion made so far? How do you find? Just pause the video and try. Yeah. Coming to the solution, fx of x equal to integral 0 to x e power temporary variable minus eta d eta. We all aware of it. That is why? Because the given function is density function is e power minus x for positive values of x. Therefore, I am taking density function distribution function equal to integration of density function. So here I can derive the distribution function of existing random variable fx of x, right? That is 1 minus e power minus x. Now my intention is to find the distribution function of new random variable, right? What do I need to find? Fy of y, which is nothing but p of y less than or equal to y. But what is the relation given for y actually? Y equal to x square. I am substituting here. That is p of x square less than or equal to y, or p of x less than or equal to y. So, but what is p of x less than or equal to x? 1 minus e power minus x when x is greater than 0. But here I am supposed to consider p of x less than or equal to under root y. If I substitute there, I can write the distribution function of the new random variable as fy of y equal to fx of root y, or 1 minus e power minus root y. Simple method. That is, new distribution function is derived. Understood? Easy method to solve. For example, let us take one more problem. Let the random variable x has the probability density function fx of x. Find the probability density function of y equal to t of x equal to cx square. Density function is not given. Only just the function is given like this. Only fx of x is given. You are not given like fx of x equal to an exponential function or any uniform density function, or any density function is not given. Generally it is given as fx of x, but the relation in the transformation is given y equal to t of x equal to cx square. What are you supposed to find here? PDF. In the previous problem, CDF is given. Now you are supposed to find PDF, right? Just pause the video and try. Yeah, coming to the solution. So here, for deriving the new density function, first, whether the relation is monotonic transformation or non-monotonic transformation must be known. First, y equal to cx square. In the sense, y equal to x square means a parabola. So if it is a parabola and one way it is decreasing, another way it is increasing. So in between y and x, what is the relation I have? That is parabola in the sense, what is the relation I have? Is it monotonic? No, it is non-monotonic transformation. In the non-monotonic transformation, ultimately a single element in the new random variable will be in correspondence with multiple elements in the existing random variable, right? So therefore, ultimately here the new density function can be derived by using this equation. That is summation n fx of xn dt of x by dx, where x equal to xn. Already we have derived this relation. So what are you supposed to take now? Fx of xn is already given in the data. You are supposed to find what? dt of x by dx. What is t of x? Must be taken here. dt of x by dx. Right. So first, y equal to cx square is the given data. So from this, I can write, can I write x equal to plus or minus under root y by c? Yes. Now, what is small x1 and small x2 here? Why? Because I have only two possibilities, either plus root y by c or minus root y by c. Therefore, one element in the new random variable is having in correspondence with two elements in the existing random variable. Since it is parabola, so ultimately one element may in connection with 2 points, right? So therefore x1 equal to under root y by c, x2 equal to minus under root y by c. One element y1 is in correspondence with two elements x1 and x2 in the existing random variable. Therefore, but now if I take dy by dx, why? Because what is the required one here? dt of x by dx. T of x is nothing but y. So I need to find dy by dx or dt of x by dx. Y is what? Cx square, which is equal to 2cx. But what I need to find? dt of x by dx, where x equal to xn. In the sense, I need to find dt of x by dx1, dt of x by dx2 also. So therefore, see that dt of x by dx when x equal to x1 is 2 into c into x1. But what is x1? Under root y by c. Therefore, 2 into c into under root y by c or 2 root yc. Fine. Am I clear? Next, similarly at x equal to x2, 2c into minus root y by c or under minus 2 under root yc. So therefore, finally I can write the density function as equal to fx of x1 by mod dy by dx1 plus fx of x2 by mod dy by dx2. Substitute here fy of y equal to fx of under root y by c by 2 under root yc plus fx of minus under root y by c by 2 root yc, or in the short form I can write, that is common denominator I have fx of under root y by c plus fx of minus under root y by c by 2 root yc, right? So this is the way to derive the density function of new random variable in the non-monotonic transformation. Fine, right? So now the new thing is next topic. So far we have discussed about random variable, right? And how to find or how to do the operations on the single random variable, and how to find the statistical parameters like statistical mean, mean square value, variance, standard deviation, skew, by finding the moments, maybe by using the moment generating function or characteristic function, right? And also we have seen how to apply the transformation on single random variable. But in the real-time scenario, we cannot expect only one random variable out of one real-time experiment. Therefore, here we are going to discuss about vector random variables. So in the sense, one experiment can be defined by using multiple number of random variables. In that case, how do you define multiple random variables? And for the multiple random variables, how do you define distribution and density functions? And all the things we are going to see here onwards, right? First, suppose two random variables x and y are defined on the sample space. Two random variables where specific values of x and y are denoted by x and y respectively. Then any ordered pair, two random variables, but any ordered pair xy may be considered as random point on the xy plane. Earlier only random variable, element of the random variable. Now combination of two random variables, and the combination will give one element from x, one element from y, will form a random point. Random point. The point may be taken as a vector random variable. Earlier only element. Now it is random point. So that random point may be taken as vector random variable or random vector. And the sample space of x and sample space of y together is called joint sample space, SJ. Right? The plane of all the points xy. Why? Because if I have x, earlier, for example, random variable x is having the elements x1 to x10. Random variable y is having the elements y1 to y10. All the combinations x1 y1, x2 y2, x1 y2 all together will form a plane, right? And the plane of all the points in the ranges of x and y may be considered as a new sample space. New sample space. For example, it is in reality a vector space where the components of any vector are the values of the random variables x and y. Repeat, in reality, a vector space where the components of any vector are values of the random variables. That is, if I take any vector, that vector consists of what? Values of random variable x and y, just as shown in the figure. The new space sometimes is called range sample space or two-dimensional product space. For example, here S2 is the sample space of one experiment or one event. It is another sample space, and one random variable is defined here as y, and one random variable is defined as x, and the combined random vector can be represented as x of s1 comma y of s2. And this particular plane which is having all such points is called range sample space or two-dimensional product space. Understood? Right? So here onwards we are going to discuss, or we are going to consider vector random variables, not single random variable, right? Or for example, in this way also I can take, for example, here I have A and B two events, and it is the combined event. And for this sample space, for one experiment, this is the sample space. For other experiment, this is the sample space. I am taking the combined sample space, right? A intersection B, and it is the random point where this is x less than or equal to x comma y less than or equal to y. In this way also I can take, right? So now we have seen what is vector random variable. Vector random variable in the sense, when vector random variable will come into the picture, whenever multiple random variables are taken to represent any random experiment, right? Multiple random variable, the combinations of all the elements of the random variables are called random points or random vectors, right? So now for the random vector which is having the combination of all the elements of the random variables will form ultimately a space, right? A plane, right? So therefore, for the multiple random variables, whenever the experiment is defined by using multiple random variables, to analyze the probabilistic models, I need to define joint distribution and joint density function. For a single random variable, we know how to define distribution function and density function, right? If there are more number of random variables, how to define distribution and density functions, right? So coming to the joint probability distribution or joint distribution function in short, right? The probabilities of the two events A, where A equal to x less than or equal to x and B equal to y less than or equal to y, are called probability distributions denoted by fx of x and fy of y respectively. We know that, and are given by, how do you give a relation? Fx of x equal to p of x less than or equal to x, right? If they are discrete, summation p of xn u of x minus xn. Similarly, fy of y equal to p of y less than or equal to y, summation p of ym u of y minus ym. These two are distribution functions of the two random variables x and y. Now if I take the probability of joint event x less than or equal to small x and y less than or equal to small y. Why? Because the two random variables are related to the same experiment. Which is the function of x and y is called joint probability distribution function and is denoted by fxy of x comma y, denoted by fxy of x comma y. Therefore, it can be written as fxy of x comma y equal to p of, be careful here, p of x less than or equal to small x comma y less than or equal to small y, which is nothing but summation for xn, that is n equal to 1 to n, for ym m equal to 1 to m, p of xm comma ym. What is this probability? Nothing but joint probability. P of xn comma ym is called joint probability. Why? Because x is one event, y is one event. Am I clear? Event here is x less than or equal to x is one event, y less than or equal to y is another event. Therefore, I am taking here combined probability, or in fact joint probability, into u of x minus xn into u of y minus ym, right? So this is the way to define the distribution function. Similarly here, if I have n number of random variables, if it is not limited to only two, then I can also write the distribution function like this. The joint distribution function for n number of random variables is, if x1 to xn are n number of random variables, I can write the distribution function like this. P of x1 less than or equal to x1, comma x2 less than or equal to x2, up to xn less than or equal to xn. Am I clear? Right? Similarly here, I can define even the density functions. How do you define the density function? Sorry, before the density function, let us move on to the properties of distribution function. What are the properties? First property is similar to the distribution function, cumulative distribution function for the single random variable, but only that case is here multiple random variable. Fx comma y of minus infinity comma minus infinity is 0, right? Fx comma y of minus infinity comma y, irrespective of the second term, this will be equal to 0, and x comma minus infinity is 0. Am I clear? Right. Fx comma y of infinity comma infinity is 1. Maximum value is 1. Minimum value is 0. Maximum value is 1. Similar to your cumulative distribution function of single random variable. Now, it is also distribution function here also lies in between 0 and 1. Minimum value is 0, maximum value is 1, right? Similarly here, it is a non-decreasing function of both x and y. So in the cumulative distribution function of single random variable also, that is a non-decreasing function. The joint distribution function is also non-decreasing function, and almost all the properties are same, right? So if I want to find the probability of joint probability of two events, one is x1 less than or equal to x less than or equal to x2, y1 less than or equal to y less than or equal to y2, I can use this relation by using distribution functions. Fxy of x2 comma y2 plus fxy of x1 comma y1 minus fxy of x1 comma y2 minus fx comma y of x2 y1, right? The last property is fx comma y of x comma infinity equal to fx of x. That is called marginal distribution function, or fxy of infinity comma y is fy of y. These two are called fx comma x and fy comma y are marginal distribution functions, right? So these are all properties of joint distribution function. First one is minimum value is 0, fx comma y of minus infinity comma minus infinity is 0, maximum value is 1. It is non-decreasing function. You can find the probabilities if you know the distribution function, right? So here in the multiple random variable case, we have discussed what is a vector random variable, and we have discussed what is joint distribution, and also we have discussed the properties of joint distribution, right? We'll continue the next class with joint density function. How do you write the joint density function for the multiple random variables will be discussed in the next class. Thank you.